Hello, so today we'll be presenting our machine learning pipeline for classifying satellite disaster imagery across two tasks. The first being disaster type classification and the second being damage level assessment. So why automate disaster assessment? When a disaster occurs, emergency agencies need to rapidly assess what type of disaster occurred and how severe the damage is before deploying their resources. And conducting a manual review of satellite imagery is not only extremely time consuming, but highly inefficient. So our goal here is to automate two decisions or two key decisions. The first being, is the disaster a flood or a fire? And the second being, how badly is the area damaged? We're working with overhead satellite imagery from three natural disasters, Midwest flooding, SoCal fire, and Hurricane Matthew. The data set that we're working with contains 600 training images, specifically 200 per disaster category, each at 1024 by 1024 pixels with 3 RGB channels. Each image is labeled with a damage level from 0 to 3, indicating no damage, minor damage, major damage, or destroyed, respectively, within that scale. So immediately here, we notice a significant class imbalance problem. Hurricane Matthew only has six major damage images out of the 200. So this comes up to about 3%, which will directly constrain our task B model. Our exploratory data analysis revealed that disaster types have visually distinct color profiles. So flooding images are blue-green from sediment-laden water, and fire images are or appear to be gray and ashy, while hurricane images are comparatively greener from intact vegetation. And this separation is also visible in the KDE distributions, but particularly in the blue and green channels, which we believe suggests that the color features alone might be sufficient for task A. So for damage levels, however, we see that the findings or the bigger picture here is very different. When we look at mean RGB intensity by damage level, there's no apparent clear trend. So all four classes fall within a narrow range with no monotonic type of ordering. So this immediately also tells us that task B will be harder, meaning that color features won't separate damage levels the way that they separated disaster types. So it'll be more challenging than task A. And combined with the severe class imbalance shown here, task B requires a fundamentally different modeling approach. So rather than using raw pixels, which would give us roughly, basically 3 million features per images, 3 million features per image against only 400 training samples, we engineered compact interpretable feature vectors. So for task A, we built 64 features across 4 groups, the RGB channel means and standard deviations, the HSV statistics to decouple color from lighting, normalized RGB histograms to capture intensity distributions, and Stowell edge statistics for texture. For task B, we extended this to 96 features by adding 32 local binary pattern bins. The LBP captures microtexture patterns, whether the pixels are lighter or darker than their neighbors, which we actually also expected to carry structural damage signals that the color alone could not. So for both tasks, we trained logistic regression as a linear baseline and random forest as our primary model. For task B, we additionally evaluated gradient boosting. So all hyperparameter tuning use macro F1 as the scoring metric, not accuracy, because accuracy is misleading under class imbalance. We used a 5-fold stratified cross-validation throughout, ensuring each fold preserved the class ratio present in the full training set. Smote oversampling was applied inside each fold for task B to address the major class imbalance. And here I'll transition to Pamela to go over the results.
All right, thank you, Camila. So as she said, I'll be taking you through our results and analysis for the tasks A and B. So for task A, both of our models performed very well. Our logistic regression model achieved a cross-validation macro of 0.99, which outperformed the random forest model at 0.973, and even an ensemble of both models at 0.988. So the fact that the simple linear model won is in itself an interesting finding because it confirms that the two data disaster types are linearly separable in our feature space, and this is consistent with what we found in our EDA. And on the out of fold evaluation, logistic regression misclassified only 4 out of 400 images with an RC area under the curve of 1. For our feature importance analysis, this confirmed that the HSB saturation mean was the single most discriminative feature, which accounted for 18% of the total importance only. And this makes sense because fire images are desaturated and ashy, while flood images retain rich color from water and vegetation. The saturation captures this cleanly without being confused by light scene variation. The RGB histograms dominated overall at 71%, while the subtle edge features contributed less than 1%, as the texture adds nothing when spectral separation is already near perfect. Our learning curve shows cross-validation F1 still rising at 320 training samples, given that the model is still data limited. With more flooding and fire images, we expect to push closer to 0.9 accuracy, the 0.98 accuracy threshold. The training CV gap of 0.01 for the logistic regression model also confirms that there is no meaningful overfitting in our modeling. For task B, this tells an entirely different story because our best model, which was the gradient boosting, achieved a cross-validation macro F1 of only 0.498 compared to 0.99 for task A. And every model achieved exactly 0 F1 on the major class because it had 6 training images and no oversampling strategy we implemented could manufacture enough signal for a learnable class. So the confusion matrix shows that the model does reasonably well on the destroyed class at 0.84 F1, but it struggles to distinguish no damage from minor damage classes. And these classes are adjacent, and they look visually similar at global feature resolution. The weighted F1 of 0.7 tells us a more optimistic story. It shows that the model handles the 3 well-represented classes reasonably well compared to the underrepresented major class. Now to our bias and variance assessments for task B. The learning curves are the most important diagnostic for task B because all 3 models show a completely flat CV F1 line, and this adds more data, and adding more data that won't make any difference. This is a high bias, not high variance, because the bottleneck is feature expressiveness, not the data quantity. Unlike task A, where the curve is still rising, here the handcrafted global features have hit a ceiling. This simply cannot capture the localized structural differences that distinguish damage levels. So, in conclusion, putting both tasks side by side, the constraint is instructive. Task A was a color problem at 71% of importance, as 71% of importance came from the RGB histograms, and task B was a texture problem given that 49% of importance came from the LBP features we added specifically for this task. This validates our feature engineering decisions that we made earlier. We added the local binary patterns or LBP for the right reasons, and the importance analysis we did confirmed this. The fundamental lesson here is that not all satellite classification problems are equal. The disaster type leaves a global spectral footprint, and damage level requires localized spatial reasoning that global statistics alone cannot provide. So, now for conclusion and feature work. We believe that task A is effectively solved with handcrafted color features and a linear model, but task B is constrained by the major class and by the limits of global image statistics. Our clearest path forward for task B is a CNN-based feature extraction approach where we replace the handcrafted features with learned embeddings from a pre-trained network like the ResNet 18. This would capture the localized structural patterns that our features currently cannot capture. Another promising extension can include finer spatial tiling beyond our 2x2 quadrant experiments, a grayscale co-occurrence matrix texture features. Now, this isn't just for us, this project isn't just a machine learning project because the output of these models informs real emergency response decisions, and getting it wrong means the wrong resources go to the wrong places in a disaster, and this can cost lives. So let's discuss a few societal impacts and ethical concerns. First of all, asymmetric cost of misclassification. This is a big problem because not all errors are equal. Misclassifying a flood as a fire doesn't just hit our F1 scores. It means that the wrong subdivision gets dispatched. So understanding damage severity means underestimating damage severity means underallocating resources to communities that need them the most. Second is who bears the risk. The communities that are most likely to be harmed by model failure are those that are least represented in the training data. So if our model was only trained on one geographic region per disaster type, it may fail precisely in the places where it gets deployed to help. So the path to a more equitable Deployment means having more diverse training data, geographic validation before deployment, and designing our systems with disaster response practitioners who understand the operational context. Thank you for listening to our presentation.